The last topic of this chapter is a very brief overview of energy. Now, in reality, you could have an entire bachelor's degree and PhD studying energy and how it relates to chemistry. This is what we would call thermodynamics, and there are, in fact, whole PhD programs based on thermodynamics. We are going to take maybe 2 videos, maybe. We might even be able to fit it all into one, we'll see, to talk about energy here. So we are very much skimming the surface. But we will still do our best here to understand energy and how it relates to chemistry. So we're going to start off here just talking about what exactly is energy and what forms can energy take. In general, energy is the ability to do work. That is kind of the broadest and most basic form or definition of energy. It's the ability to do work. But there's lots and lots of different types of energy. So, for example, there is kinetic energy. This is energy associated with the movement of objects. So, for example, in baseball, there's lots of kinetic energy. You have the ball being thrown at high speed. You have the bat being swung at high speed. You have the two colliding, and you have this pretty significant exchange of kinetic energy there that deforms the ball and the bat when they come together. So kinetic energy is just energy associated with moving things. Anything that is moving has a certain amount of kinetic energy. There's also potential energy. This is energy associated with the position or composition of an object. And potential energy is a very, very broad category of energy. There's lots and lots of types of energy, but the two most common ones that you hear about are gravitational potential energy, and then chemical energy is actually also technically a potential energy, but we'll get back to that in just a second. So gravitational potential energy is associated with essentially how high above the center of the Earth something is. So the higher up, the farther away from the center of the Earth, the more gravitational potential energy something has. Electrical energy is associated with the flow of electrons. So if you have electrons moving through a wire, there is a certain amount of energy that is associated with that movement. Thermal energy is something that everyone has. This is energy associated with random motion of atoms and molecules in matter. So just because something is at a certain temperature, it will have a certain amount of thermal energy. And the higher the temperature, the more this thermal energy it will have. And then the last one there listed is chemical energy. This is associated with the position of particles that compose the system. Like I mentioned a minute ago, technically this is a subcategory of potential energy, but it's usually mentioned in its own right just because it's a very large category of energy all on its own. So molecules and how the atoms in those molecules are arranged, there is a certain amount of energy that is associated with those positions and how the atoms are positioned relative to one another. Alright, so when we're talking about energy, it's important for us to be able to quantify how much energy something has, and anytime we're quantifying something, we need a unit. We need a unit to describe and to compare from one thing to another how much energy something has. And there's 2 main units that are used for energy in chemistry anyway. There is a third unit that is used quite a bit, and that is the kilowatt hour here, but that's mainly just used for measuring the amount of electricity that your house uses. Really, really large amounts of energy could use a kilowatt hour. For our purposes, where we're just dealing with relatively small amounts of energy, like the amount of energy that would take place in a chemical reaction that's happening in a beaker, we will use either joules or calories. Those are the 2 main units that are used. The joule is possibly more often used. They really are actually both used very, very often. When I was in school, the calorie was used more when I was taught anyway, and it seems like joules are now used more often, which I'm not actually entirely sure why that's the case, because calories are actually a little bit friendlier, I think. At least in my mind, they're a little bit easier to work with. But they are both used relatively often. The conversion from one to the other is given right here. So 1 calorie is the same as 4.184 joules. So the calorie is about 4 times as big as the joule, which is why it takes a little over 4 joules to be the same as 1 calorie. The calorie that we're seeing here is related to the calories that you see on any food items you might have in your house right now. But they're not the same, actually. So the calories that are listed on your food, those are actually what we would call kilocalories, or kcals, or just food calories. And when I'll talk about those, I will just call them food calories, just to be absolutely clear what I'm talking about. And a food calorie is actually 1,000 of these regular, so to speak, calories. So 1,000 of these calories with a lowercase c is the same as 1 food calorie. And as far as I'm aware, the only reason for this is just because food companies decided at some point that it sounds a lot better to say that a Mountain Dew has 170 calories. That sounds a lot better than saying it has 170,000 calories. It's a lot smaller number when you use the food calories, and so it doesn't sound quite as intimidating. But like I said, they are related in 1,000 to 1 conversion here, and we'll most often use just these normal calories or the joule. But if you own a house or you pay the electric bill at wherever you live, you're probably used to seeing kilowatt hours as well, because that is how your electric bill is measured, is in kilowatt hours. And the kilowatt hour is much bigger than either a calorie or a joule. 1 kilowatt hour is about 3.5 million joules, as you can see here. So it is much, much bigger than a joule or a calorie. So real quick here, I think we'll call it for this video after this question, and we'll finish up in the next one. How many joules are in a 2,000 food calorie diet? Because that is the normal, I'm not sure what government organization it is that puts that stuff out, but the average person is supposed to take in about 2,000 food calories a day. Now, 2,000 food calories, how many joules would that be? Well, if we have 2,000 of these big calories, I know how many normal calories there are per joule, and I know how many normal calories there are per food calorie. So I can just use 2 unit conversion factors here. So for every one of these big C calories, there are 1,000 little c calories. And then for every little c calorie, there is 4.184 joules. So, if I measure that out, or calculate that, 2,000 times 1,000 times 4.184, that would be, and I'm actually going to put this in scientific notation, that would be 8.37 times 10 to the 6 joules. So about, not quite 8.5 million joules. which is apparently a little over 2 kilowatt hours. Since a kilowatt hour is 3.6 times 10 to the 6, that would put us a little over 2 kilowatt hours, which is kind of weird to think about. That it's, the same unit that you use to measure how much electricity it takes to run your house. You can use that same unit to talk about how much energy it takes to run you. Because, I mean, if you think about it, you really are just a very, very complex biological machine, at least scientifically speaking. We're not going to get philosophical here. And it takes energy to run even biological machines. And we get our energy from eating hamburgers or fries or our Frosty here. Our bodies then take in those molecules from the food, and they convert those molecules into energy, which is kind of crazy and kind of cool when you think about it. Alright, we'll call it there for this video. I'll see you in the next one, and we will talk about endothermic versus exothermic reactions and finish up with talking about heat capacity.